Okay, I'll begin by taking a look at the problem that I created for this example. We have a street sign and traffic light hanging from the horizontal column. The horizontal column is attached to the vertical column at 20 feet up. The weight of the vertical column is 400 pounds. The weight of the horizontal component is 200 pounds. The weight of the state sign is 50 pounds, and the weight of the traffic light is 100 pounds. All the members of the system are assumed to be of uniform density, and we're asked to determine the magnitude and direction of the resulting force couple imposed by the system on the rigid joint at O, which is this point right here. So, as I mentioned in the guidelines, we're going to break the process into smaller steps. First, we're going to examine the problem. We're going to note the givens and what's asked of the problem. Next, we're going to draw a free body diagram. We're going to choose a reference point. In this case, we're going to choose our origin of axes to be at the point O, this point, at the rigid joint. Then we're going to draw the forces acting on the free body and include the magnitudes, points of application, and the directions. Then we're going to relabel the distances of the vectors with respect to the new chosen reference origin. Finally, we're going to calculate the resultant force and the moment resultant of the forces about O. The resultant force is just the combination of the sum of forces in the x and the sum of forces in the y. And the moment resultant is the sum of the cross product of r by f. So at this point, you can go ahead and examine the problem, note the given characteristics, and determine what is asked of the problem if you just pause the video now. Okay, so I went ahead and did that. The givens were the weight of the vertical column is 400 pounds, the horizontal support is 200 pounds, the state sign is 50 pounds, and the traffic light is 100 pounds. The words uniform density imply that the weight of each component is applied at its center of mass. We're asked to find the force couple at O, which is the resultant force and the moment resultant about O. Step 2. Draw a free body diagram. We're going to choose a reference point, our origin of axes. That will simplify this process for us. We can choose any point. However, in this example, for us to stay on the same page, I'd like to ask you to go ahead and choose this point at the rigid joint O as your origin. Draw and label the force vectors acting on the rigid body, the free body. Include the magnitude, points of application, and direction. Then relabel the distances of the force vectors to the new chosen reference origin. So you can go ahead and, looking at this, draw a free body and label the forces and the r distances from the new origin of axes at O. Okay, so I went ahead and did that. Here we have, since they were of uniform density, all the forces act at the middle of the objects. So this 50 pound acts where the middle of the sign was. 200 pounds acts at the middle of this horizontal beam, and the 100 pounds right here acts where the middle of the traffic light was. And this negative 400 acts straight down. That's the weight of the vertical component. So using the principle of transmissibility, which says that we can take this point of application and move it anywhere along our line of action, and it'll result in the same moment about O. So since these are parallel with the y-axis, moving these down here won't change the distances from this axis. However, this original distance was 9 feet from the end of this column to the force, but we had to add an extra 0.5 half foot because now we're referencing from the center of this column, and it was a foot wide. So redirecting these vectors down here and applying them here will give us our r values, because these are now perpendicular to where we're looking for our moment about O. So R1 here, crossed with F1, it's R1 is 0 feet, so R1 F1 is just going to be 0 feet. However, now you can go ahead and calculate the sum of forces in the x direction and the sum of forces in the y direction, and then calculate the sum of moments about O of the cross product of the vectors, which would be R1 cross with F1, R2 cross with F2, R3 cross with F3, and R4 cross with F4. Okay, so I went ahead and did that. Step 3, we calculated the force and moment resultants about the rigid joint O, which was the sum of the forces in the x direction were actually 0. No forces were acting in the x direction, as you can see. The sum of forces in the y direction, however, all of the forces were acting in the y direction. So we have negative 400, minus 50, minus 200, minus 100 is negative 750 pounds J, which is the y component. Since those were the only forces acting, that's our resultant force as well. It's negative 750 pounds J. And then to calculate the moment resultant, we took the sum of the R by F cross products. R1 F1 was 0 feet I by negative 400 pounds J, which is 0. I by J is K. So that's just 0K. Product of these was negative 475, negative 2100, negative 1850. Units were pound feet, and the directions were all K. Negative K directions. So that's our moment resultant. That's these two combined are our force couple answer right here. So that's all they were asking for, but if you just to take a look at what that would look like. So basically, we had forces up here, 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 and here. This one moved straight down. However, to move these ones over, we had to multiply them by the R, because so this is the sum of all the forces here, and this moment right here is the moment that these would have created had they still been up here. So moving them down here, we had to add this to balance out what's really going on. And that's it. So just to reiterate, going back over the steps, just to enforce them, we examined the problem, note the givens and what's asked, drew a free body diagram. We could choose our reference wherever we'd like. We drew the forces acting on the free body. Relabeled the distances for our R values for our cross product, and then we just calculated the force and moment result. Yeah, that's all. Hope this video was helpful, and thank you for your time.